Welcome back to the online video lectures of computer vision. In the last couple of classes, we discussed about computing the transformations from one image to the other image. And then for example, if you know that this is a translation, how do you compute that? Then of course, if there is a rotation, how do you do that? And then rigid transform, right? Euclidean transform, affine transform. These are the transforms that we have looked at. And to a small extent, that homomorphic transform also we have looked at. And after that, we have also seen how to represent it, this transformation as a matrix. That's something we have seen. And then we have also seen like how many degrees of freedom would be required for each of those transforms in order to compute them, how many sets of pairs of points are required, right? That's what we discussed. And then another thing we did is, for example, you are able to compute this transformation. You have more points than what are required to compute this transformation, right? So then there is a different subsets of points that you could choose in order to compute this transformation. Then how do you choose the right transformation? Because each one might give you a different, slightly different, if not very different, and some being very different depending on which subset of points you have chosen. This again, I could illustrate whatever I'm saying right now from this picture. Assume that I took the picture by translating my camera, and then I would like to find out the transform between these two images, such that, let's say I want to stitch these two images and align them and bring a panoramic view there. So what can I do? So this in a way connects various things that we have been discussing from more than last 10 classes, where, for example, you would start with key point detection, then you would do key point description, and assume that you know there is only translation happening when you are moving your camera. Okay, this is just one assumption. So each set of points would give you, in fact, once you describe the point, you could find out a nearest match to that and assume that those matches are given by these lines which that particular point is mapping in the other image. There could be some false matches here as well, we can expect, and there could be points for which there is no matches, and all these possibilities are there. Now the question is, in the last class and class before that, what we discussed will help us. For example, if there is a translation and I give you the corresponding points here, it will tell me how much is the translation. But the scenario that we have here is we have more number of corresponding points than what is required to compute the transformation. And added to that, there is also a possibility that some of these pairs of matching points are not the right matching points. Okay, because the key point might not be, whichever is there in one image might not be there in another image. Then when you are mapping it to a nearest point, you might have ended up in mapping it to a wrong point. That's one possibility. And another possibility is because of the variations in the illumination or variations in the viewpoint itself, you might be getting some wrong matchings. So under all these conditions, how do you compute a transformation? Now we are moving, notice that now we are moving, let's say, at least in this example, from finding out matching or transformation from one point to another point to finding out a matching or transformation from one image to another image based on the transformations of a given set of key points. So how can you do that? You, for example, there is a point xi, so I would first let me start with that and then gradually see if there are any issues with that, and then we go further. So this was the last slide of the previous presentation. Suppose I have x2 point here. Okay, now assume that my this I know this parameter p, which, for example, is giving me, let's say, ax2 plus b. Okay, just I wanted to introduce some translation as well as some scaling kind of stuff to x. Okay, assume for the time being x2 is a vector you could think of, and a and b also vectors you could think of, but that's good enough for some intuition. Now what could happen, this ideally should match to x2 dash. If you are, see here, I'm computing this parameter, one parameter for all the points. Or it could also be the case where, let's say, I have in this case a triangle here that had moved here, and for that triangle to move, there is some parameter you are getting there, which would transform it to the other parameter. I think the matrix, you all remember that 3 by 3 matrix, right? But when you are looking at the individual, when you are looking at the individual points, this might not exactly match with x2 dash. So what you could do is, for example, I could vary I from, let's say you have 1 to n points, and here I take ax2 plus b. It is different. Ideally it has to be x2 dash or a times xi plus b minus xi prime. Okay, subtracting that, this ideally has to be 0, but it is having some value. And this being a vector, let me take an L2 norm of it. Okay, and this, let me do it for all I varying from all n points. This is something I want to minimize. Okay, and of course I could pose it in slightly in different scenarios. I could accordingly modify it. For example, here I assume these are all the points here. So let me just, even I could avoid here the vector notation. Let me call those points are xi comma yi. Okay, on one image, and another image xi prime comma yi prime. Okay, and assume that I figured I need to find out the x naught, the translation. Let's say, yeah, translation, let the translation be x, in the x direction be x naught, and y direction be y naught. Now can you guys tell me the equation how it should be there? Let's say I have the points from 1 to n. Okay, now you tell me the equation now. Okay, just a small modification I do just to avoid square root, the norm square also I would take. Now you translate this into this 2D problem here where there is a simple translation. What is it that, so this is something I would minimize now here. Okay, in this minimization you compute a here, a comma b, if this is the case. Okay, now you tell me the equation here, give it an attempt here.
Is it just xi plus x naught equals
xi
xi
plus
dash?
x naught,
X naught minus xi dash.
xi prime, and then
This norm, the norm of this whole square,
don't
we have
use
to
norm, just tell me in vector, in scalar form.
whole square. Whole square, we have to minimize this particular.
Is that all? Y
Okay,
is also
even
there.
sorry, by yeah, sum of.
So shall I, can I keep plus here?
Yes.
Okay, then
yi
That's y.
naught
mm,
minus yi prime
mm,
also.
mm. So minimize, what are my parameters to be minimized here?
X naught and Y naught.
That's all. Is this clear to everyone? I'm just simplifying the problem. I'm not using matrix notation at all to make things simple. So xi plus x naught is actually should be ideally xi prime, which is not the case because of this x naught and y naught could be slightly different from each point. So the distance, the difference, so the error I'm getting in x direction is this, in y direction is this. L2 norm of a vector, if I'm taking that square root of the square, this difference square plus difference square, and then I need to find out x naught comma y naught. Is this equation intuitive and clear to everyone? This is very important. If we don't understand this matrix representation, and doing that will be even more complicated. Now, how do you compute x naught now?
Differentiate with respect to x naught.
That's right. You differentiate with respect to x naught. Correct. So you need to, you write it as xi minus xi dash. Okay. And then of course so you have two terms here. If you see that contain xi minus xi dash is essentially a constant value. That has nothing to do with the parameter x naught. So a plus b whole square, a square plus b square plus 2ab. So here you would be getting 2 times x naught. Okay, x naught square term, 2 times x naught. Okay, if you write it as minus there, then you would be getting 2 times x naught into this, so that you would be getting 2 times xi minus xi prime minus xi, something like that you would be getting. That's your and of course there is a summation here. Okay, that's you should be able to solve these kinds of problems. I leave this as an exercise for you. If I give you these points, if I want you to compute this, you should be able to do it. I'm just giving you an outline here. So how do you know whether it is minimum and maximum? You find out another derivative and make it to, and depending on the sign and other things there, okay, you make it to 0, substitute here, that would tell you whether it is a minimum and maximum. Of course that would be minimum. So then similar case you could do for computing y naught also. Okay, if this intuition is there, then you could scale up to matrix representations. Okay, so that's what we were doing here. You have variable varying points I. For all points you are taking the L2 norm. Okay, this just by keeping that, it means it's an L2 norm you are computing. Then f of xi, on this you are applying p. That's earlier, if you look at, that's equivalent to, for example, since I have just translation, that was xi plus x naught, yi plus y naught. Okay, again keep in mind that this is a vector, while I was here using a scalar notation. That has to be clear to you. Okay, that's why of course this L2 norm representation. So f of xi comma p minus xi prime, the square of it. Okay, this is, as you could see, is predicted location. Xi, x naught and y naught, if you take xi plus x naught is a predicted location. What is xi prime? This is a measured location that you want to go there, and then you are taking Euclidean norm and you are squaring it, so that you could get rid of the square root in the L2 norm. This is referred to as a residual. Residual, that's something that got remained after subtracting that, the residual, or projection error. Through this matrix you are projecting one to the other, but there is some error that you are obtaining there. That's why this is also referred to as projection error. Okay, so yeah, what are the variables here? This again the same question I am repeating. So these p is the variables that you need to find out. So argue, that's why now you write this problem as that which minimizes p. So you compute these parameters here that minimizes this residue, right? And of course this summed up or all points that you have there, and that you call it as p hat, right? And then of course ax equal to b, that's how we have been used to looking at this expression. Okay, solving set of linear equations that give you ax equal to b. But be clear here, there is a flip of variable name notations that we are using for variables. Here usually ax equal to b, these are the parameters to be computed, whereas for us a and b are the parameters to be computed here. Okay, this x is not the parameter, p is the parameter. Okay, that you don't confuse that with the ax equal to b. This x is nothing, is not, is actually opposite to the x that you are using here. This x is what is a here, and p is x here. Okay, that b is xi here. Okay, that's, anyway, just pay attention to that. So essentially this boils down to the classical problem of solving a set of linear equations where you usually have more number of equations than the parameters to be solved. Okay, and again The way we are solving here using least square errors is only the basic algorithm. There are again quite a lot of variants to this algorithm, which is out of scope for this course, because if we start looking into that, it would take at least two, 3 classes to have a fair look at the different algorithms. Like for example, one algorithm could be, you would assume that from the noise that getting added to the solution of ax equal to b is Gaussianly varying. So from the fit, you vary it with sigma. That also you include here with that variance and other things. Anyway, we are not going to deal with that right now. This is good enough for our purpose here. Okay, this is but at the same time, remember, suppose sometime if you want to include it, don't think that this is the best way to do it. Just be aware, know that, and be informed that there are better variants of this which you might use if your problem to be solved requires something like the least square fit. Okay, then earlier it was pretty easy to look at things in a scalar form. That's what we did with the translation, and we have written it as a square root of x, the translation in x whole square plus translation in y whole square. But you should be also be very comfortable and familiar with representing all these things in the matrix form also. For example, we just now noticed that this is equivalent to solving ax minus b, where a is a matrix. Okay, for example, this could be a matrix of a could be the parameters that you have. Okay, so this parameters, and then sorry, a is the set of values that you are having. X is something parameters which you need to compute there, right? So this can be ax minus b whole square is what you wanted to minimize, right? By varying this x values here. So this, how do you write this in matrix form? Square of it is nothing but ax minus b, the transpose here, right? So then you expand that. So that's equivalent to, um, how do you then write it? So this, for example, this is equivalent to ax whole transpose minus b transpose multiplied with ax minus b. Okay, and this is equal to x transpose a transpose minus b transpose multiplied with ax minus b. Then you do a multiplication here, this term with this term, that would give you x transpose a x. Okay, this a transpose a comes here, right? Then this term would be equivalent to this multiplied with this, would give me x transpose a transpose b minus b transpose a x. Okay, minus b transpose b. Notice this would be a scalar quantity at the end of the day, these each of them. So look at that, these two being scalar. When you have a some value, some p, when it is a scalar, p transpose will be equivalent to p. You use that property and you would see that these two quantities are same. So you just keep one that you could write as 2 times here. That's how you would get 2 times x transpose a transpose b. B transpose b is again, he could be written as an arm of b square. Okay, and to minimize the error, you set the derivative to be 0. Okay, I leave that matrix part. This is a very standard one. You look into any Wikipedia or any standard textbook, you have it. So that you would get essentially this anyway doesn't have any term with respect to x, because that's your parameter here. So then you would get here a transpose a times x would be equivalent to a transpose b. That's you would be getting. So then how do you solve this equation? Suppose, and then of course if you take second order derivative, you would know that this would give you the minimum value. So given this equation, you multiply both sides with 8. So for example, if I have ax equal to b, to solve that, what I can do one way. This is not the way in practice you would be using, you may be doing it differently, but here you multiply both sides with a inverse, and then this is in fact equivalent to identity matrix. So that's how you get the value for x equivalent to a inverse a inverse of b. In the similar lines, a transpose a inverse you multiply, and that multiplied with a transpose b is how you are going to get the solution for X. This is how you use linear least square fit for computing the global parameters or overall parameters, which is a kind of average of all the individual parameters that you are getting from each point.
So is this X more like computing the average X, or uh, what exactly does this X
Yes,
represent?
that's what. See, essentially the name as it says, you are finding out a transformation X such that it minimizes sum of squares of differences that you are getting for each individual point. So I think the better explanation intuitive explanation you get from the simple case here, as I have written here. So this is something, the error sum of squares of errors that you are getting, which you are summing up over all n points. That's what your x naught and y naught are, such that it minimizes, it's not an average, it minimizes sum of squares of differences that you are getting over all the points for that given transform. See, if it has been an average, it is very simple, 1 by total number of points into xi minus x naught, that's how you could do. But here what we are doing is, you are minimizing, these are the vector forms, it's not a simple one there. So this is how you are doing it here. Hoping that this is clear for all of you, is what is the problem with this approach? What is the problem that this also we pointed out? We have some hints in the last class. So what is that? If I, yeah, well, again, let me show you this figure. So what do you think if I am doing in this manner and computing the transformation, what could be the problem here? Mappings which were not correct. Say, for example, while these got mapped here, maybe this might have got mapped to something somewhere which is wrong. Now look at what this is trying. This transformation is a kind of, if you ignore that, I assume that the right set of, so this could have been very nicely getting mapped there. But because of these cases which were wrongly, so this assume that this is getting mapped to somewhere here, but that would bring this minimization problem that would make it to converge to some other x naught and y naught. And if this value is too high or too low compared to what all most of the pairs of points are giving, then this could bring an undesirable change in the minimum value to which this is going to converge to. This is one important problem. Second problem, this inherently assumes that all the points have same transformation, undergoing the same transformation. There could be a scenario where, for example, not this image, but perhaps an image where objects are moving, and each object might be having a different transformation, and then you obtain the key points and trying to do this. Then since it assumes same transformation for all the points, that's bound to give you wrong results there. So these are the, among others, perhaps these are the two important issues that you have with linear least square fitting to find out the transformation. Is that clear? If you don't have questions, I would put one more question to you. Then how do you think you can address this issue now? So is the problem clear to you? If not, the solution? What could be the problem that could end up this whole situation into a undesirable or a wrong answer, wrong minima? So is that clear to you all?
So just to clarify, the two statements you made was, one was on moving objects, and other was being the wrong key point matching, right?
Correct. That's right.
Okay.
So more than moving object, I will say that different regions in your image have different transformations. But if you are doing a single transformation, fit everything that you are trying to optimize the equation that I have written there, then that is going to cause a problem. That anyway, even the next algorithm still has that same limitation, so I don't want to highlight that at this point. That we will come a little later in the later classes. But I would say here the key problem that at least the next algorithm is going to address is that suppose there are points which are getting wrongly mapped. Okay, there is for some reason it found a key point there, assume. Okay, see these 3 points, if I'm doing this when the distances are maybe 1 point here which is moved yeah, I should, yeah, uh, well, this actually is images. Okay, don't interpret the length there, it should, because if you keep the point there then the distance is small, but I mean the length, assume that that's the translation rather than the mapping there. Okay, so if there are at least few points that are diverging from a common set of from the points that are having more or less same transformation, these two guys, these few guys could corrupt the entire stuff. So now, how do you think you could address this? Assume that my parameter is a single, this to simplify the whole stuff, I'm taking a trivial example. So now don't think in terms of the transformation matrix translation rotation, but consider a simple case. I want to fit a line. I got a set of points. So if you want to even now pose it in the other problem, it is like your degrees of freedom is 2, right? Slope and intercept. And then you have to compute it from the set of points. Now, if I have this set of points, when you see visually all these points, you could say very easily that look, these two guys are outliers because all these points are here. So then you would say I would fit a curve like this. But if you give it to least squares, if these 2 points were not there, it would have done a very similar job. But the moment, so inherently what we are doing here is you are able to first segregate or classify which are inlayers and which are outliers. Basically, in layman's words, outliers are bad data. Maybe your correspondence, it got mapped to a wrong thing, there is a noise there. Points that do fit are inlayers. So first, once you compute that, you could then nicely fit a curve like this. But on the other hand, if you give, so that's something like this, it would, so that would be, for example, if you take in layers and out layers, you might fit something, separate them and just try to fit here, it would fit something like this. But the moment these two whole, your sum of squares of differences getting modified, that might fit something very different. Okay, I could in fact have few more and make it completely come out of the scope. That's quite possible. So this is what your general least square fit would, once you have these 2 points. But ideally, if you remove those 2 points, then you would get this one, which is in perhaps what you really want. Okay, so that is what now we are going to do. Well, as one of you rightly pointed out, the first step now would be to detect which are outliers. So how do you think we can detect which are outliers? And anyway, just to, for the sake of completion, let me also tell you one scenario where this is how it is. It's not just, you don't know how many lines are there, but intuitively once you see it, you could say that, well, I would prefer fitting a line here, fitting a line here, and fitting a single line doesn't make sense, you would know. But if you use least square fit, that would fit something like this. This is what we would do later in motion estimation. This is one problem. As I said, different things might be having different velocities. Okay, displacement vector, velocity vectors. In that, this cannot yet be figured out by the algorithm we will be discussing right now. So we will postpone this problem to later classes. But for now, we would focus on this outlier issue. Okay, where you still have a single, all of them would fit into same set of parameters. That's our assumption. Coming back, so um, uh, as you rightly said, you first classify data points as outliers or inlayers and fit a model to inlayers while ignoring the outliers. Okay, this is again this work by Fisher, Fischler. I think I'm not very sure of the pronunciation. Sorry for that. That's 1918, a long back work, but a very classical work. You would be able to appreciate it more by the time we finish going through it. A very, very solid work. Say, for example, it has almost more than 25,000 citations if you in Google Scholar, if you look at right now. Okay, so that also should tell you how significant and pioneering this work has been. Okay, so let me pose you one question here now. How do you think, consider this case itself? Okay, now how do you think we could detect inlayers and outlayers? I would like to see some tries from you guys. Okay, trying to figure out how this can be done. I'll give you this set of points that you see here. Okay, maybe this is even better. And now you need to figure out which are outlayers and which are inlayers. How do you do that?
Sir, we can. It's slightly computationally intensive, but we can first calculate the least square error, the regression line, and then whatever we calculate the distance from that line to all the points.
Okay.
And then whichever points have maybe a distance above a certain threshold, we can remove all of them and calculate the line again.
Yeah, not at all a bad idea. You don't mind getting this fit first, and then you look at which are very far from here, and then you consider them as outliers. That's what your idea is, right?
Yes, sir.
Good. I don't want to do even that. That's a nice idea. Okay, that works to a good extent, but I don't want to do the least square fit here. Any better way of doing it? That's definitely something that would give you definitely better than what the original result is. But I would like to see without doing any least square fit. I'll give you a hint here. You have more number of points than the points required to fit a line here. So can you somehow exploit this and come up with an approach? I'm again stating that all you want to do is fit a line here. The number of points that you would require to estimate the parameters for a line are pretty small compared to the number of points you have here. So can you exploit this somehow?
We can start with any arbitrary line. So
Very
this line will have some parameters like y equals mx plus c. It will have one slope, it will have an intercept.
Right.
Now what we'll do, we'll measure the distance of each point from that line, or we'll take something that's more like anything related to that, basically some sort of distance. Now what we have to do is we have to minimize the sum of these distances.
Right.
So if we are minimizing the sum of distances, or we have to minimize something, some particular, whatever is the reasonable parameter in any given case.
Right.
Now to do that, we can start by iterating over every time. Like first we have a random set of parameters. Once we know, like after first round of iterations, we know that the distances, we know some particular distances.
Right.
We'll use it to adjust the line parameters. Then we'll keep on repeating that till we reach one particular segment. Basically like a sort of regression.
Excellent. Very good. It's almost close to the final answer. Very good. Very well framed. See, I will slightly rephrase it and make it more systematized, but the answer is right. How many points do you require to fit a line? 2 points, right? So from the whole set of points available, you pick 2 points, fit a line. Okay. So for example, I happen to you can randomly pick points. And then for example, I picked these 2 points. My line is something like this, right? Now to this line, assume that I consider any point within a given distance. For example, on this side, this, on this side, this could be more formal, but I'm doing it first an intuitive way here. Those points which are within that distance, I consider those points within that region as inliers and the rest as outliers. So for example, now I might be getting 4 points here. Then what I do, I think I have nice slides for that. Again, stolen from the internet. I don't exactly remember, but most of these slides are from Professor R. N. Bobbick. So anyways, so 2 points you take, you fit a line there. From those 2 points are good enough to fit a line. Then you take a distance, a measure, you know that within this distance, if something is there, you consider it as inlayer. So now you have 4 inlayers for this set of 2 sets of points. Now again, randomly pick 2 more points. Those are the 2 points, for example, now you picked, and again you put that. Now you got inlayers as, let's say, 6 inlayers are there. Now you pick another 2 points. Now you see the number of points are 19 are there, barring maybe outside 1, 2, 3, 4, 5, 6, 7 points are out, 19 points are within that. And you repeat this whole process for sufficiently a large number of times. You repeat this experiment. Okay, what is sufficiently and all these things, that paper, RANSAC paper, is going to deal with it very elegantly. We are going to see that maybe in the next class. Okay, yeah, for sure in the next class. It will take quite some time. Okay, so this you got 13. Now you have, for example, first one set of,
Sir, can you just repeat what you said?
yeah, so I'm repeating here. Look at here, I took a set of points. I am randomly picking 2 points out of the whole lot of points, whole set of points that I have. I'm picking 2 subset of 2 points there randomly, and based on that points, I know the slope and intercept. You fit a line, and within a specified margin to that line, you consider it as inlayer. So first set of points that you picked, you got, let's say, 4 inlayers, 6 inlayers, then 19 inlayers, and then 13 inlayers. So then obviously the one with 19 inlayers and the rest being outliers is a best fit. So you are going to consider this slope and intercept as the final slope and intercept. And you could notice here, while fitting this curve, you are not bothered about, for example, these points which are for some reason got wrongly mapped to. And this is exactly what RANSAC does. Outliers should be outliers, so it should not be like more than inlayers, for sure, right? If the noise is more than the content, there is nothing you could do there. So you have more number of points, sets of points, than the points required to fit a line. So you pick just those number of points that are required to fit a line. You fit a line and see how many inlayers that has. You repeat the whole process by randomly picking couple of points from, let's say, a pool of 20 points. And finally, pick those those 2 sets of points for which you got maximum inlayers. And whatever the slope and intercept that you are getting from those 2 points is the slope and intercept that you would assign for figuring out the transformation, or in this case, for drawing the line. How many times you have to pick the points? Can we say some limit on that? How do you figure out what's the margin there? Is there a better way to fit a line than these? Are the questions I want you to think about. I'll tell you, for example, I want to say with a 90% of probability, let's say, or 99% probability, I want to say that I hit the correct set of points. I hit the correct values of the parameters. Is it possible further to know how many times I need to repeat this experiment of picking the points? That's one question. Okay, so that I want you to think about it. And suppose further to compute, I would give you the information of our assumption, if not information to begin with, which is not bad, is, let's say there are 90%, only 10% outliers are there among all the points. So then can you tell me how many times I have to repeat this experiment such that I will pick, I'll randomly pick, okay, because this will be able to say for sure I will randomly pick with, let's say, 99% probability the right set of points. And this way I found for the set of points, this is the slope that I'm getting for the 2 points that I have picked. But is there, given that these are the inlayers, is there a better way to fit the curve? These are the questions that we would be answering in the next class. Okay, so I will just take 1 or 2 minutes more where I will just formalize. This is again from Forsyth and Pong textbook on computer vision. So I will introduce you to the the names of these parameters or variables and put it in a more systematic way so that you think about it and try to get what is the, how many times I need to repeat this experiment, given that I have, for example, 10% of outliers and I want to pick with 99% probability. I want to say that I got the outliers correctly, I got the inlayers correctly, or I did the experiment correctly. This is the question I'll be leaving you with. But to write that answer, you need some proper terminology to use, and all the parameters and variables to be there. So n is the smallest number of points required. Say for example, if it is a line, you require 2 points here. Then k is the number of iterations required. This is number of times you need to repeat the experiment. T is the threshold used to identify a point fits that well. So that's where you are seeing, for example, in the simple case, the distance from the line. Okay, that's the threshold, you keep it there. D is the number of nearby points required. So for example, I would say, if I say I have 10% outliers, once I fit it, and if there are 90% of points are in layers, that's where I can stop my experiment. So that's telling, that is given by the D. Now you, what you do in general is number of iterations required. You figured it out. This is what I want you to figure out, how many times I need to repeat this experiment. This is a classical stems from the classical probability and basic probability. You don't need to know hi-fi stuff in the probability. I want you to think about how do you compute this k. Okay, you come up with that. Okay, and then until k iterations have occurred, draw a sample of endpoints from the data uniformly at random, fit to that a set of endpoints. Okay, outside the sample, against this threshold you consider as outlier, inside as inlayer. If there are more than d points, percentage of your inlayers is more than that, then that one, or in other words, you repeat this experiment k times. Whichever is having maximum number of inlayers within this k, you take those as your final parameters. Okay, I leave you with this. I want you to think about, these are the things I am giving you. I will say that I want to know with, let's say, a probability p could be, for example, 99%. If I repeat this experiment capital N number of times, where my sample has, okay, I don't mind showing you once this, but still if you could decode and come up with the answer, I'll be pretty happy. Okay, E is the probability that a point is an outlier, number of points in a sample. So for example, if it is a line, as I said, I need 2 points here. Capital N is the number of samples, it is number of times I need to repeat this experiment. P is the desired probability. I want to say with 99% of probability I now have the right parameters. So then I want to compute how many times I want to repeat this experiment. This would be equal to, you could note down this answer, and I would be happy if one of you explains me why this is the case. 1 minus of 1 minus of 1 minus e whole power s whole power n equal to p. Okay, where the world did that come from? I would like to hear some. I'm sure some of you, if you put your minds into that, I'm sure you'll be able to do that. Okay, we'll stop here and see you in the next class. Bye.